let's move on. Our next topic is the reserved word in materials science is stress. We use stress all the time, especially inside college. We talk about a stress headache, or I'm feeling stress. Stress, as defined for materials science, is simply this. It's simply the force that we just talked about, the load. But what we're going to do is, rather than talking about how strong or how large was the load, we're going to be talking about how large was the load divided by the area of application. So in this case, it looks very similar to pressure. Pressure is just that, force over unit area. But when we're talking about taking a piece of material, like in this case, this purple cylinder down here may be an aluminum rod, and we're pushing it against a plate, or maybe this is a pencil pushing against a piece of paper. We're simply talking about how strong is the force and how strong is the contact area that we're actually interacting the material with. So it really is pressure. We're going to borrow this concept from physics, force per unit area. If you recall our physics stuff, the base unit for force is in newtons, and the base unit for area is square meters. So in SI, or the scientific units, we're going to be using newtons per square meter for stress. And in the case of the English system, or the imperial system, we're going to use pounds for force and square inches. So we're going to get pounds per square inch, or PSI. So in this case, when we talk about the stress that a material is under, it really is going to sound like how much pressure is this material under, and what sort of pressure does it take to make this material change its shape, or how is it reacting. Okay, so again, we use stress all the time. I have a stress headache. I feel like I'm under pressure, trying to have, my schedule is not long enough for me to get all these things done. I feel like I'm being forced to do things. I feel like I'm being jammed into a small little area time-wise. That's why humans like to use the word stress when they talk about feeling stress or being under a stress headache. It's they're borrowing it from the materials scientists. So very, very closely related to stress is what happens to the material when you do stress it. What happens to a material when you do put a load on it, when you start to pull it or you start to push it. And many times, depending on how closely you can measure it, what happens when you push or pull on a material is it starts to change size. What happens here, I have a little illustration of this little rod here. It's a blue little rod. Obviously, it's just a rectangle in this picture, but it's a blue little rod. Here is the original length. And then what we're going to do is we're going to pull on this thing, and we're going to stretch it. And as we stretch it, this thing sort of gets longer and longer and longer. There's our change in length. And now we're going to have a new length. So the original length was L0 at time 0, going back to our physics notation. The new length is L, and of course there's a delta L there. So in this case, what we're going to do is we're going to find out where you are now, how long is the L, minus where you were before, divided by where you were before. So if you recall all the words that we used for delta back in our physics class, that's what delta is, where you are now minus where you were before. Rather than just talking about the change in length, we're going to ratio this back to how long was it to begin with. So this is our official definition of strain. It is simply the change in length, where you are now minus where you were before, divided by how long were you before. So that's our official measurement. It turns out that there's no units for strain. If we were measuring this in meters, we would have a change in length of a couple meters, compared to a few meters original, and meters divided by meters is 1. It goes away. So it turns out that in engineering we call this a dimensionless number, or in this case a dimensionless ratio. So strain does not have a real cool unit like pounds per square inch or newtons. It's just strain. But we do give it a symbol. We don't give it an S for strain. We give it this epsilon for strain. So this is the symbol for strain for all these materials. When we push it or we pull it, if we pull something and it gets longer, then it's straining, and it's straining as it gets longer. And if we push it and it gets squished, then we're straining it as it gets smaller. Going back to how we use the word strain every day as humans, we have lots and lots of materials. We're made out of materials, and especially for those people who are on sports teams and have worked out, if you pull a muscle too far, So the muscle has a normal size, and then you pull it so far that you actually start to stretch it. Then we have what's called a strain. So you can go ahead and have a strained muscle or a strained tendon, depending on what material it is that you've stretched. So stress is how much force per unit area, and strain is how much does it change when we are stressing it. Okay. So those two things of stress and strain really do go well together, and that's sort of the basic thing that we're going to be doing for most of the semester, especially in the laboratory when we measure how much a material stresses and strains. In this case, we're going to measure how much it strains, how much longer does it get, or how much shorter does it get squished as we pull or push on it. So we're going to turn this into a y and an x axis, or an x and a y plot. The x-axis, or the horizontal axis, is going to have our strain. That's going to be how far does it change size. And then the y-axis is going to be how far, or how hard, how large is the value of force per unit area. And then the data in here is simply a measure of where that shows up. How hard are we pulling on it or pushing on it, and how much longer or shorter how has it gotten. And when you plot that on here, it turns out that materials typically follow this very, very generic cartoon of a curve. We're going to see in a second what we mean by an elastic region and a plastic region, and fracture. We'll see that in a second. But what happens is typically materials follow in a straight line. The harder and harder we push or pull, the longer or shorter they get. And then eventually we start pulling them and stretching them beyond their limit, and then eventually they snap. So in this case, if this really is pulling on something, you can see this material is getting longer and longer and longer, and eventually it starts to get super longer, and then eventually it just breaks. And the same thing happens the other direction. If you squish something down, maybe it's a spring, the spring starts to squish and squish and squish. Eventually it starts to squish non-linearly, doesn't follow this nice pattern, and it breaks as well because you squished it by pushing on it too hard. We're going to come back to this in a few seconds, but this is the basic measurement that we're going to make in the lab when we actually test the material for strength. How strong is it? And that question of how strong is something, again, is based on how well, or what is its reaction when you stress something. We measure its strain, and then we ultimately find out when it breaks or fractures. So these are called destructive measurements. We really are going to take materials, put it in a machine, and do something nasty to it with stress and strain until it snaps, and then that's going to be called a strength measurement or a stress versus strain measurement.